Okay, where's on what intervals is this decreasing and concave down? So this is kind of a 2-for-1. To know where it's decreasing, I would figure out where it's changing directions or might be changing directions, critical number. So you have to take the derivative. Don't forget chain rule. So that is probably the most important part, because if your first derivative is wrong, it doesn't really matter how much time you're going to spend on it after that. So are we okay with that being the first derivative? Okay, so critical numbers are going to be when the first derivative equals 0, which would be at x equals 0, makes the numerator 0, or undefined. What numbers make the denominator 0?
Square root of -1.
Okay, but square root of -1 is not going to show up on a graph, so we wouldn't keep that one. So this is the only place that might be changing directions. So to know if it's increasing or decreasing to the right of this, you should be testing something to the right of 0 into the first derivative. Positive over positive is positive. Test to the left of the critical number. You need to test the left and right of every critical number for increasing, decreasing. We would get negative over a positive, which is negative. So if the question was only about decreasing, my answer would be what?
Negative. The negative infinity to -1. That's where it's 0.
It goes up to 0. -1's the point I tested.
Yeah, sorry.
But if it's decreasing at -1, it's going to decrease this whole time, all the way up to 0. Okay, well, I also need to compare that with where it's concave down, because I want to know when is it decreasing and concave down. So to find out concavity, we need second derivative. So I've got first derivative right here. Second derivative, we would need the quotient rule. Derivative of the top with the bottom left alone minus the derivative of the bottom with the top left alone, all over the denominator squared. And for your own sanity, you might want to simplify this a little bit. Maybe just call this -2x squared plus 2 over that. Okay, so you surely should have known that you needed the second derivative. Is that what you got for the second derivative?
Yes.
Okay. So concavity changes at inflection points. Inflection points occur when the second derivative is 0 or undefined. That doesn't mean that those are inflection points, but that's where inflection points come from. So where the second derivative equals 0, since this is one nice big fraction, that's nice, it's going to equal 0 when the numerator equals 0. So that would be when x squared is 1. So that would be what?
1.
When x equals 1? Good, plus or minus. You take the square root of both sides. You have to do plus or minus. You can see how important that is. Now, in my opinion, again, you really need, most of this is not just about justification points for an FRQ, but a lot of this is organizing your information. You need to label what you think this is. That's what's supposed to help you. This might be, maybe, an inflection point. And this one may be an inflection point. It's not confirmed to be an inflection point unless the concavity changes. Not that that matters anyway. This question doesn't ask anything about inflection points, but since we're here, we might as well talk about it because it'll help later when they do ask about inflection points. Okay, to know the concavity between these, inflection points are the places where the concavity might be changing. So we should try something like 0 in the second derivative. We would get positive over positive, which would be positive. And when the second derivative is positive, it's concave up. Throw in a number like 2 into the second derivative, we would get negative over a positive, which is negative, concave down, and okay, so does that make x equals 1 an inflection point or not?
Yes.
Okay. So I can cross off the word maybe now. I can see that the concavity changed. Okay, over here, I could test maybe negative 2 into the second derivative. So that would be negative over positive, which would be negative, or concave down. Notice on my little line chart here, you shouldn't be thinking I'm adding much more than you should be. This is concave up because the second derivative was positive. This was concave down because the second derivative was negative. Now that I can see the concavity change at x equals negative 1, I can cross off this word maybe. I know that it is an inflection point now. To be an inflection point, it has to change concavity. Okay, so if this question was only about where is it concave down, well, it's concave down from 1 to infinity. That's this stuff. It's also concave down from negative infinity to negative 1. But the answer to our question is it wants to know when is this function decreasing and concave down. So basically, where do these two overlap? So what would that be?
Negative infinity to negative 1.
Negative infinity. Why not 0?
Because it's not concave down to 0.
Very good. It's not concave down at 0. This one is between the times. It's definitely decreasing. It's definitely concave down. From 0 to negative 1, it's not decreasing. From 1 to infinity, it's concave down but not decreasing. It's only both of those things during that time. Negative infinity to 0.
Negative infinity to negative 1. Yeah.
I'm sorry, negative 1. Negative 1. Negative 1 is the more restrictive one. Okay, so a lot going on in that one, but I had to think about where it's decreasing and increasing with first derivative, where it's concave up, concave down with second derivative. The derivative was a little bit harder. It had chain rule. Second derivative had quotient rule. Again, those things don't go away. They just don't happen as frequently. But any final questions about number 7 before we wrap this one up?